The Best of Our Knowledge explores topics on learning, education, and research. Coming up, a monster molecular cloud has been discovered in our galaxy that was not previously known to exist by a team of astronomers. This cloud is made up of gas and dust and is about 200 light years long. Whoa, that is indeed a monster. We will learn more about this cloud and what exactly it is and its functions. You're listening to The Best of Our Knowledge. I'm Madeline Reynolds. Did you know that clouds could be monsters? In size, of course. Well, a team of astronomers have discovered a molecular cloud in our galaxy that is quite giant. This cloud was not known to exist as it was found in a little-known region of our Milky Way galaxy. The cloud is made up of dust and gas that is about 200 light-years long. This cloud revealed to the astronomers that it is a dynamic region of bustling activity that includes possible star formation. I spoke with Natalie Butterfield, an assistant scientist at the National Radio Astronomy Observatory, to learn more.
All right, so these giant molecular clouds are thought to be kind of the building blocks of spiral arm structures in the Milky Way galaxy and in external galaxies. And they're really thought to hold a lot of the molecular material that's associated with the galaxies. So these giant molecular clouds are, by definition, very, very large. So they are usually on the order of about 10 parsecs or so, up to hundreds of parsecs. Usually once you get kind of towards that upper end, you start to get to like the larger spiral arm structure. But essentially they're kind of the building blocks, and multiple ones together can form these like spiral arms. And so the cloud that we were looking at is about 60 parsecs. So it's well within that range of what you would expect for a giant molecular cloud. And it's very massive. So we measured using dust observations towards the source. We measured a mass of about 100,000 solar masses. And so typically with GMCs, you get solar masses or masses of about 1,000 solar masses up to, almost 1,000,000, depending on how big this thing is. So we're well within like the range of what you would expect for a giant molecular cloud. Now the properties, so you can get properties of giant molecular clouds from different types of observations. So using dust continuum or using spectral line or molecules to kind of measure kind of the velocities within the cloud. So by using spectral line observations, clouds or moving objects can have what's known as Doppler shifts. So that's where, as an object is moving towards you or away from you, the way that you would have a ambulance. So if you have, if you're hearing an ambulance that's coming toward you or a fire truck, you can kind of hear the pitch change as it's moving toward you or away from you. And so you can do the same thing with light. And so these molecules in these clouds give off what are known as spectral lines. And by looking at how much they've shifted, you can kind of understand the velocity. So we've used these spectral lines to really understand just kind of the internal structure of how the gas is moving within the clouds, how, you might be getting some shearing or where it's being pulled apart or maybe like where it's getting stretched. And so using these kinds of molecules, we can really understand the internal structure. And so that's kind of one of the things that we looked at in this paper was like understanding, okay, well, what is the internal structure of the cloud doing? Are we seeing it shearing? Are we seeing it being pulled towards like the galactic center? And so being able to use these different observations, not only the new ones that we presented in our paper, but also ones that were from archival data. So there's been a lot of surveys across the Milky Way galaxy. And so we use this archival data in addition to our new data to really kind of understand these various properties to say, okay, well, it fits, within the mass and it fits within the size and it fits within the kinematics. And so, yes, this fits exactly with what we would expect for a giant molecular cloud.
So no one knew that this cloud existed, this one that you studied specifically. So I'm wondering, why is that? And just how did you discover it?
Yeah, so just to backtrack a little bit, so the larger galactic bar dust lanes, so these are the larger features that are associated with the Milky Way's galactic bar, were first observed back in like 2008 and like the early 2000s, but it was like very, very broad. Like you saw just like kind of the large arm, essentially. It was relatively quiet. Like since that paper came out in 2008, like no one really studied it. No one had really looked at it since then. And then there was part of my team had looked at this back in 2019, where they had like used some of that previous 2008 data, and they're like, oh, well, they basically started to get kind of the conversation going. And so me, in addition to them, had looked at the midpoint. So we said, okay, well, we know kind of where a lot of the CO is. We kind of know where the larger structure is. Now we see this really kind of like pocket right here. Let's go in with some higher resolution data and just see what it looks like. And so that's what we did. So we said, okay, let's target, this kind of bright spot that we see in the dust lanes, like the larger dust lanes. And we went in with the GBT, and sure enough, we saw this large, giant molecular cloud. And we really kind of like the reason why, well, there's two reasons why that we wanted to target this one in specifically. So one is that we wanted to, one, target the midpoint. So this was, kind of like you kind of know the properties in the galactic center, you kind of know the properties in the disk. And so this is kind of like the midway down. So you kind of see, okay, well, you have kind of the edge, you have the center. So now what does it look like kind of towards the middle? And so that was one of the other reasons why we wanted to target this cloud and specifically. And so we got some time on the GBT. We said, okay, let's take a look at this cloud in higher resolution, and sure enough, it just glowed. So yeah, it was really kind of like surprising. Like we, maybe expected to see a couple pockets, a couple just kind of dense clumps, not the entire large structure that we ended up seeing. So that was really kind of like when we got that first image, it was just like, oh, this is amazing. Like what, who knew that this was there? So it was really kind of a really interesting result that came out of that study. And I guess one of the other issues that you have with observing the galactic bar dust lanes is that they are kind of a little bit tilted. So you've got like, if you're thinking of kind of the generic picture of like the Milky Way galaxy, you kind of just get this like band across the sky, and it kind of, is this, kind of just like line that you kind of see across it's the plane of the galaxy. And so a lot of previous like surveys of the Milky Way galaxy really kind of cover just the center part. And so because the dust lanes kind of tilt a little bit, if you can kind of see there, so they kind of tilt a little bit. And so because they fall just a little bit below the galactic plane and they have a really extreme velocity, so it means that, again, that Doppler shift, it's really extreme. And so a lot of these surveys targeted just the plane and then targeted just around 0 kilometers per second, which is where you expect disk gas to be. And so just because of that extremity, you just don't, like, it wasn't really included in a lot of spectral line surveys. So no one knew that this was associated with the dust lane. So again, they have the continuum observations, the dust continuum, and yeah, it looks like a normal cloud when you look at the continuum, but it's when you apply the spectral line information that you realize this thing is actually just accreting into the galactic center. So it really kind of makes it stand out against the plane of the Milky Way.
You're listening to the best of our knowledge. I'm Madeline Reynolds. If you're just joining us, we're learning all about a giant molecular cloud with Natalie Butterfield, who is an assistant scientist at the National Radio Astronomy Observatory. I would love if you could explain more about this midpoint cloud. When I was reading about it, I wasn't sure if that was just, the signifier for the midpoint of this giant molecular cloud, or if there was other things to it that was also important and what it does for the bigger the bigger area of it. Yeah.
No, that is a good question, and actually one that we had in our internal collaboration was like, what do we call it? Like we've discovered this new source, like what do we call it? And so we had a few conversations like, do we call it the sine wave cloud, because you kind of see this kind of like, sine wave looking pattern, and we're like, no, well, maybe that it like implies some type of like oscillation in there, and we don't know if that's true or not. And so we kind of like ruled out a couple like possible names, and we're like, well, let's just, we know that it's at the midpoint, we know where it is, in the dust lanes, and so let's just call it the midpoint GMC. But Yeah, we had some like internal discussions of like, what do we call this? Like, what would be a fun name? And like, looking at different wavelengths to see, okay, well, maybe it looks kind of like an elephant. You can kind of see the trunk, and there's this like clump on the side. Maybe that's the ear. And we're like, no, well, there's already an elephant name in like astronomy. So it was kind of like a little bit of back and forth of like, what do we call it? Like, we've discovered something new. We get to name it. Like, what are we going to name it? So we've kind of left it as the midpoint GMC right now, just because that refers to its location in the dust lanes. But I mean, we might have some other papers coming out, so we might try and find a fun name if anyone has suggestions.
In your research, it also outlines how the cloud shows signs of star formation. So I'm wondering if you could just provide more details about that for us and the evidence you collected to prove that.
Yeah, yeah. So there's two sites of possible star formation within the cloud. One is associated with the source that we called not B, and then this other one was a source that we considered not E, which was at the very end. So the two sources that we have really showed up in continuum. So this is again where because the cloud is located so low in galactic latitude, so below the galactic plane, we don't really think there might be too much contamination. But again, because it's continuum, there is kind of this like small kernel of like, okay, well, is it maybe just something along our line of sight? Like we think it is star formation. We see it in the Spitzer telescope 8 micron observations. So those are thought to be associated with really hot dust. So you have like these protostars and they're kind of like ionizing and heating up the dust that's around them. And so they glow at the really kind of mid to short infrared wavelengths. And so we saw this kind of like cluster of compact sources in there. So we think that that is like an evidence of star formation. But again, because it's only in continuum, we kind of just left it as like, oh, we consider this a possible site of star formation because we really want to have, again, the spectral line information that's coming from that source to say, oh, it's at the same velocity that we have of our cloud. And so we know that they're located, within the same structure, within the same galactic stream. So we did want to, I guess, follow up and do maybe some ALMA observations or even like JWST observations to really get a nice picture of it. But we do need to have the spectral line information from those sources to say, oh, yes, we know that this is, associated with the GMC. They have the same velocities. They're at the same location. And therefore, you kind of have that extra bit of evidence to say that, yes, they are together. So we did kind of present it as saying, hey, this is the line of evidence for saying that it is a star formation site. But again, because it is continuum, you always have to have that, I guess, just that little kernel of just unsurety of saying, okay, well, we do want to double check this before we are, as a confirmation of saying, yes, we've, proved it. So we had that source, and then there is the other source that I mentioned was not E. And so this one was actually pretty interesting. We've actually done some follow-up observations already with ALMA, and they support some of the conclusions that we had in our paper. So the conclusion that we had for that one is that there seems to be this kind of like compact source, and it shows up not quite at 8 microns, but it shows up at 70 microns, so a little bit longer, kind of more towards like the mid, slightly far infrared, but it still is kind of associated with hot dust. And the interesting thing that we see about this is we see this tail coming off of it. So we see this kind of glowing tail. Yeah, so it almost kind of looks a little bit like a comet where you have the head and then the tail coming off of it. And we did some follow-up studies with ALMA, and we're currently writing this up, but it shows a very similar structure where we have this compact source and then this tail. So we do, and that's all at the same velocity that we expect for our cloud. So we do know that this source is associated with the GMC. And so now we're kind of working through the properties of the star formation, say like what could be causing the wind? Like we see this tail, like where's that tail coming from? Like why is it almost perpendicular to the direction of infall? Like does that mean that there maybe is another nearby star formation site that's blowing the wind up and that's what's causing the tail? So we are investigating, I guess, what it means to see this kind of head and tail like structure. But we were able to do follow-up observations for that source and have shown that it shows the exact same thing that we were presenting or hypothesizing in our study.
So it also says in your research that within the cloud, the gas is turbulent. So I would just like you to tell us what that means.
Yeah, so turbulence really kind of comes from that internal structure, like the internal motions within a cloud. So turbulence is really kind of a way of understanding just how kind of like mixing the gases. And so when you get like, if you have like a cloud that has really broad or really wide lines, really broad turbulence or high turbulence, then that means that there's a lot of motion that's going on in there. Now, where that motion is coming from, so you could have just a lot of like maybe like different components, and like because your beam is like larger, that you might have stuff that's like you have different components in there, and each one of those is just slightly offset from each other. And so when you combine them all together, you get this really broad component. So there's a lot of different things that could go in to producing broader turbulence or higher turbulence. So gas mixing is one. You could have shocks. So if you have like feedback, so let's say you have like a star formation site in the center of your cloud, then that's blowing the material away. And so you kind of get all of these different components in there. And so you get this really broad line width. And so when we were going through and investigating in our paper, we saw that all of our different sources and all of our different clumps within the GMC show these really broad line widths. And so that means that there's likely some type of internal mixing, internal structure within these clumps within the cloud. And typically, when you're looking at the galactic center versus the galactic disk, so a lot of clouds in the galactic disk they have very, very thin line widths. You're kind of just moving along, as you're orbiting, around on the Milky Way galactic disk and you're orbiting around, you're not really interacting with a lot of other clouds or clumps. You're just kind of in your own spiral arm. Whereas in the galactic center, you get a lot of mixing, you get clouds collisions, like everything is kind of within 100 parsecs. So you get a lot of dense gas that's moving around and like orbiting around and hitting other clouds. And so the fact that we end up seeing broad line widths at the midpoint that are comparable to what we see in the galactic center suggests that maybe during infall you're getting this stirring, you're getting this kind of stretching, you're seeing types of like maybe cloud collisions, you're seeing a lot of dynamics already at the midpoint, even before the gas accretes into the galactic center. So that's really one of the interesting things, I guess, with this study is that it's a way to kind of understand the initial conditions before gas accretes into the galactic center. And so the fact that we're already seeing really broad line widths, very turbulent clouds, suggests that maybe the clouds are already turbulent before they reach into the galactic center. And so now understanding where that turbulence is coming from, I think is one of the open questions of saying, okay, well, if we go to higher resolution, do you see that, those single clumps break up into like multiple streamers or something? And maybe that's what's causing it. Or do you see kind of a shell-like structure? Maybe that's feedback. Or do you see maybe shearing where it's being pulled and stretched and that's causing the broader alignment. So I think we really need to go into the higher resolution, the next step of going even deeper into the cloud to say, okay, well, now what's causing these broad line widths, because we've already measured that they exist and we've compared them with the galactic center. So now it's going in and saying, okay, well, why is it doing that?
So it also in the article says that we're going to go back to the midpoint cloud here. Says that it is a crucial link. So I'm just wondering what that means. What is it a link to? What is yeah.
Yeah, so the link, we've kind of referred to the galactic bar dust lanes like in general as like the missing link. Because again, like when we look at the galactic center itself is just a very extreme environment. Like we kind of refer to it as like the big city, whereas like, maybe the galactic disk is more of like suburbia, where it's a little bit quieter. It's a little bit, you kind of have your like narrow line widths. You've got, your little maybe like star forming sites and stuff. But for the most part, a lot of the gas is quiescent. You're kind of in your spiral arms, whereas in the galactic center, you've got really broad line widths. You've got a lot of pressure. You've got a lot of turbulence. You've just got a lot of like it's a really extreme environment. And so the reason why we've considered the missing link is because we don't understand why the galactic center is as extreme as it is. And so one of the questions is like, as gas is falling in towards the galactic center, are you seeing an increase in turbulence? So basically, as it's falling in, maybe it's just because it's falling into the potential well, towards Sagittarius star, towards the supermassive black hole, that you're getting just an increase in turbulence. You're seeing an increase in temperature. So a lot of clouds in the galactic center are really hot. Like they're much hotter than anything we see in the galactic disk. And so, is that caused from this infall? And so by studying, basically, if we're able to have almost like a little timestamp or a stamp of like different little clouds along the galactic bar dust lanes, do you see kind of a steady increase? Or do you see maybe like when gas like is at the edge of the bar and like has a shock and then starts falling in, like is that shock at the end where you start to see it? Or maybe is the shock when it enters the galactic center? So it's kind of that like why are the properties so different between the galactic disk and the galactic center? And so by studying the galactic bar dust lanes, we want to say, okay, are you seeing kind of a steady increase? Are you seeing maybe more shocks? Are you seeing more like heating, that type of thing? And so what we want to do is to basically study different clouds along the dust lanes to really kind of paint this picture of, okay, well, why is the galactic center so extreme? And is it extreme just because the gas entering it is already extreme? So the missing link just kind of refers to this missing link between the galactic disk and the galactic center, and the galactic bar dust lanes are that link between the two sources.
You're listening to the best of our knowledge. I'm Madeline Reynolds. I've been speaking with Natalie Butterfield, an assistant scientist at the National Radio Astronomy Observatory, all about the monster molecular cloud in our Milky Way galaxy. So, when I was reading the entire article, I thought about, how, okay, we all know stars do die at some point, right? So, I was getting along my thinking and I was curious about, does this giant molecular cloud, for a lack of a better term, ever die? I don't think that's the right word to use, but do you know if they ever kind of like disappear or dissipate? Or is that something that even happens?
You can have molecular clouds that are just blown apart. So this is typically when you get the really massive, like high mass O and maybe B type stars. So the really massive stars, they can, through their winds and even through like the supernova, just kind of expel the cloud that they were born from. So you can get this kind of feedback from the dying of stars that just disperse the giant molecular cloud that they were associated with. So we have seen that both in the galactic disk and there have been several massive clusters. So a lot of these stars will form in clusters. So we do have three massive clusters in the galactic center, and all of those are thought to be near these kind of like just large shells where they've just kind of blown away the material that was near them. So that could be, a possible future for this cloud. We could also see kind of this. So one of the interesting things that we saw in this in our kinematics, so this is looking again at the spectral line velocity information, is that we almost saw this like counter rotation. So we kind of saw a lot of the lower velocities on one side versus the other side, and it almost kind of looks like you might be getting this kind of like counter rotation towards infall. And we also have this possible gap in our longer giant molecular cloud. So you could be kind of getting one part that's kind of pulling away from the other. Again, we would probably want to do modeling. We probably would want to say, okay, well, what would that imply for the galactic or the gravitational potential as it's infalling? If you had this kind of already like the snapshot of what the velocity structure looks like, if it continues falling in, are you going to get that one side just kind of pulling away? So you could get, this cloud kind of, possibly splitting if you have like these really thin kind of filaments and you get one side that's getting pulled one way and one side getting pulled the other way. You could have, where it thins out and maybe even, separates into two that continue kind of falling in at their own, orbital direction. So one could be feedback. The other is just you are kind of infalling and you have a lot of just pull on one side. And so you get one that's just a little bit tilted, maybe from feedback kind of pushes it a little bit more in one direction, and then gravitational potential just kind of continues to carry it in that direction. So I mean, the cloud is thought to infall in the next 5 million years. So there's still some time for it to either form stars or even just kind of like start to probably wouldn't dissipate really, because a lot of these are kind of held together, through their own gravitational potential. But all you need is just a little kick in one direction or the other, and it could either collapse down and then start forming its own stars, or it could just kind of start to like be blown apart. So I think that is a good question in the sense that we would probably want to do some type of virial analysis, which is where you compare the internal gravitational potential compared to the kinematics. So again, if you have a lot of motion, a lot of velocity, that motion can kind of start to, pull the cloud apart, whereas the gravitational potential really kind of pulls it in. And so doing a virial analysis is where you kind of weigh those two. You say, okay, well, how much is it being pulled apart versus how much is it being pulled together? And, if it's greater than one, it might pull one direction. If it's less than one, then it'd be pulled the other direction. So that's not something that we had done in this paper, but it is something where that's what you would want to test, is to say, okay, where is it kind of on that tipping scale? Like, is it being weighed down or being pulled together more? Or is it being, kind of just, is that turbulence just going to start pulling the cloud apart? So I think it could go either direction. We do kind of see a couple things where it's like, okay, well, that's, the gas is looking a little bit thin right there. So, if all it needs is just a little bit pulled in one direction, and you could start to thin that out and just kind of almost pull it apart. But I think we would want to do, again, some type of modeling to really say, okay, this is the snapshot that we see. This is like the gravitational potential that it's in. This is the direction that it's going. All right, hit play. How will that, as it falls in, how is that going to impact the cloud? So I think it would be interesting to kind of see like, okay, will it survive? Will it start to like, kind of coalesce maybe with some other gas that's in the area? And what does that imply for star formation and then its future before it accretes into the galactic center?
So, my last question to you, Natalie, is what did you find to be the most fascinating aspect of this research for you personally?
Ooh, that's a good question. I guess for me, it was the most fascinating. I think the star formation complex that's in Knot B is really kind of really interesting because we kind of see this kind of almost like pillar or like elongation within these knots. And the star formation site that we see there almost fits like a glove with some of the other data that we have for the region. And so for me, I think that that one was the most, like, really the most interesting because we've haven't really studied too many clouds like individual like in detail along the dust lane, so there really hasn't been a whole lot of study on star formation in this type of environment. And so I think being able to like one see that we have a really strong candidate, again, you might have some like line of sight confusion or contamination, but considering again its location below the galactic plane, I think 90%, I think we have a strong candidate for star formation. And so that I think was really exciting. I think the star formation sites within this kind of galactic bar dust lane, within this, this really interesting environment that hasn't really been studied, I think being able to confirm that would be that would be like a nature paper. So that's kind of, I guess, the next step or the next area that we really wanted to investigate in detail is to one, understand, is that forming stars? Is it associated with the galactic bar dust lanes? And, could it be forming O and B type stars, like which could then, impact the entire GMC, which could blow it out, which could really kind of have a strong impact on the future of the cloud. So that's kind of, I think, the next steps. Again, science is always and research is always a ever ending study. So that's kind of the next steps I think that we want to do is to really investigate those in detail. We also have a large program that was approved by the GBT where we're trying to target the entirety of the dust lane to have this really nice map and to identify all of those different clumps of dense gas as it's falling into the galactic center to understand some of those questions that I had pointed out earlier about like, okay, well, is temperature kind of increasing as you're falling? Is turbulence increasing as you're falling? Or do you have, single spots within the dust lanes where maybe you've had a cloud-cloud collision, and maybe then that's okay, then it's like turbulent for the rest of the way as it goes. So it's really kind of understanding the larger properties of the dust lanes and then kind of comparing those to the galactic center and then the galactic disk.
That was Natalie Butterfield, an assistant scientist at the National Radio Astronomy Observatory. The research was originally published in the Astrophysical Journal. This has been The Best of Our Knowledge, episode 1826. The Best of Our Knowledge is a national production of WAMC Northeast Public Radio. The latest on all National Productions programs is available via the Airwaves newsletter and our flagship station's website, WAMC.org. Until next time, I'm Madeline Reynolds.